crossed the vast plains of interstellar night where starlight travels for millions of years. Without ever touching solid ground, a lone fragment drifts through the cold. It is older than memory, older than the sun, older perhaps than the conditions that shaped Earth into a living world. For uncounted ages it has wandered through a silence so profound that even cosmic rays, its only constant companions, arrived as rare needles of energy piercing a dark without boundaries. In that quiet, the object slept beneath a shell of ancient ice-layered dust in the chemistry of forgotten nebulae. Nothing marked its journey except the slow accumulation of minerals, volatiles, and molecular structures formed in the distant debris fields of exploded stars. It carried the history of other suns on its surface, though no mind had ever known it, and no world had yet recognized its coming. Then, without warning, its path bent toward a faint yellow star rising in the distance. The gravitational pull of the sun extended across interstellar emptiness, like a soft hand, subtle at first, then insistent. Over millions of kilometers, the star gathered the traveler into its influence, drawing it inward through the heliosphere, a boundary none of its kind had crossed in at least 10 million years. Here radiation increased dramatically, no longer the thin drizzle of galactic rays, but the warm, constant pressure of solar light. The object began to change. Subtle shifts in temperature rippled through its crust, awakening minerals that had been frozen in stasis since before humans existed. Shadows etched across its surface as it slowly rotated, revealing jets of sublimating gas that whispered upward into the void. But Earth did not yet know its presence. At the edge of astronomical detectability, it was merely a dim point of motion slipping across the background of stars. Yet something in that motion was wrong. Its trajectory was not bound to the sun. It came not from the familiar plane of planets or from the reservoirs of long-period comets, but from a path that no simulation could reconcile with the orbits of known bodies. It bore the unmistakable signature of an interstellar origin. In time, telescopes captured clearer glimpses. Observers noticed its unusual hues, the reddish tint characteristic of objects forged in remote, frigid territories beyond any solar system's light. Colours like those of Sedna Makemake and other trans-Neptunian bodies appeared on its surface, yet the object's course was stranger still. It had not circled a star in geological epochs. It had drifted freely through the galactic stream, accumulating the scars of cosmic irradiation, accumulating the secrets of molecular chemistry, unhindered by warmth or motion. Slowly scientists began to piece together something extraordinary. This was no mere comet. It bore a density of organics, metals, and oxidized volatiles rarely seen in anything of our solar system. Its carbon dioxide to water ratio stood far outside the norm. Its nickel to iron balance hinted at origins shared with the rarest Cr carbonaceous chondrites, meteorites believed to have formed not in the young solar disk, but in the cold aftermath of stellar birth, where materials drifted unbound before merging into larger structures. Spectroscopic signatures pointed to chemistry shaped by billions of years of cosmic exposure, mixed with volatile deposits that had survived intact in the interstellar medium. Yet these details, these fragments of truth, still rested far ahead in the narrative. Before discovery, before interpretation, before the world realized that something older than Earth was passing nearby, there was only this, an object silently crossing the threshold of the sun's domain, beginning a transformation shaped by heat after an eternity of cold. As it approached, solar wind swept across its surface like a desert gale. Layers of dusty regolith, porous and fragile, began to release carbon monoxide and carbon dioxide in thick oxidized streams. Beneath that surface, water ice waited in abundance, suddenly finding itself exposed to a radiance millions of times stronger than anything the object had ever encountered in interstellar darkness. Its rotation just over 16 hours meant that each region of the surface warmed evenly, turning the entire body into a global engine of sublimation. Jets erupted into space, forming tails that stretched tens of thousands of kilometers. Some extended outward from the nucleus in a long diffuse plume, while others emerged in puzzling sunward arcs that defied expectations. From far away the object brightened. 2 magnitudes in a matter of days. It didn't fade back as comets usually do after an outburst. Instead, the brightness persisted and intensified, hinting that the transformation was not local, but planetary in scale. Something deeper had awakened, and as the object grew brighter, Earth's astronomers could no longer ignore it. They plotted its course. They traced its past. They realized it had not passed near any star in millions of years. They understood that its chemical signature was unlike anything born in the solar system's familiar environment. By the time Earth truly noticed, it was already inbound, already accelerating toward the Sun, already undergoing changes that would leave researchers questioning whether this traveller was merely a comet or something far more ancient, far more enigmatic. For now, it remained unnamed to the public, designated simply by coordinate and year 3IATLAS, the third confirmed interstellar object ever seen arriving quietly, yet carrying the weight of a mystery that stretched across time and stars. As it sailed deeper into the inner solar system, everything about it suggested contradictions. It behaved like a comet, yet not like any comet known. It resembled primordial meteorites, yet came from distances where such bodies rarely survive intact. It carried water, yet far more oxidized volatiles than the solar system could account for. It built magnetite, hinting at reactions that demanded liquid water, at distances where water should never melt. And quietly beneath the scientific curiosity, a deeper question began to form. One whispered, rather than spoken. One that, if answered, might reshape humanity's understanding of its place in the universe. What if this object is not merely a relic, but a messenger, a vessel of chemistry? A carrier of organic seeds moulded not in one solar system but across many. In that question lay the heart of the mystery. The possibility that life or its foundational components might travel between stars not by accident, but by the natural processes of drifting objects like this one. Atlas might be the physical embodiment of a hypothesis as old as cosmic speculation itself that life does not arise in isolation, but spreads quietly, patiently through the galaxy. But all of this, the spectroscopic anomalies, the catalytic reactions, the unexpected jets, would come later in the unfolding story. Everything begins here in the silent drift of an interstellar traveller entering the light of a star it has never known. A stranger from the deep night carrying secrets older than continents and oceans, now approaching a world whose inhabitants are only beginning to understand what its arrival may signify. It was in the lull of early July, when the night sky settles into its quiet summer geometry, that an automated survey telescope swept across a small wedge of darkness and registered a flicker of motion that did not belong. The Atlas survey, designed to scan for near-Earth hazards, captured the faint streak almost incidentally. At first glance, it appeared to be nothing more than a dim, slow-moving object, its magnitude low enough to place it far beyond the orbit of Jupiter. Yet the smear of light behaved strangely. When its motion was extrapolated backward, it did not trace the wide, looping arcs familiar to long-period comets. It did not align with the cloud of icy bodies that haunt the distant reservoirs of our solar system. Instead, its trajectory resisted every attempt to tether it to a past orbit around the Sun. Within hours, astronomers began to suspect they had observed something unbound, an object drifting in from the outside. They looked again, and again. More exposures revealed its arc shallow, hyperbolic, and unmistakably interstellar. This was not an emissary from the Oort cloud. It was a wanderer from beyond the Sun's family altogether. Over the following days, more observatories turned their gaze toward the anomaly. Archival sky images were scanned for earlier hints of its passing. Some were found faint, grainy impressions in older catalogues confirming its steady inbound motion since at least the 1st of July. Its brightness was low, its coma barely perceptible, but the direction of its path defied any gravitational history with our star. It had entered the solar system not as a returning visitor, but as a foreign traveller. For the astronomers who had witnessed the first detections, the realization settled slowly. They were watching only the third confirmed interstellar object ever observed entering the heliosphere. Oumuamua had been the first enigmatic, fast and uncomfortably brief in its visit. Tus Borisov had been the second, more comet-like, more familiar yet still alien in origin. Now there was 3IATLAS, an object that seemed to echo neither of its predecessors but carve out its own category. As measurements accumulated, a picture began to emerge. The object's incoming velocity, once stripped of solar acceleration, corresponded to no typical orbital population. Its inclination placed it on a descent from high above the ecliptic, cutting across the solar system's plane like a stone skipping across a pond. And when its path was projected backward into the starfield, using the Gaia DR3 catalogue, researchers traced its trail through the galaxy for 1,000 parsecs without finding a single stellar encounter close enough to alter its trajectory. 10 million years of silence, a span during which Earth's continents shifted, species appeared and vanished, and ice ages came and went, had passed since the object likely brushed near any star at all. This discovery deepened the intrigue. If it had wandered through interstellar space for such a span, its surface chemistry would have been sculpted not by solar wind cycles, but by the patient erosive touch of galactic cosmic rays. Hydrogen ions, high-energy protons, and nuclear fragments cascading through the Milky Way would have ionized and restructured its outer layers. Carbon-rich compounds could have polymerized into long tar-like chains. Ice trapped in its matrix could have sputtered slowly away, leaving behind a fragile skin of irradiated organics. Everything about its appearance, its reddish tint, its low albedo, its inertness, was consistent with such a history. But what no one expected was how rapidly it would transform once it crossed deeper into the sun's embrace. Before that metamorphosis began, however, its discovery initiated a global effort to characterize it. Telescopes in Chile, Hawaii, the Canary Islands and Australia coordinated observations. Spectrographs captured faint emissions from its coma, revealing signals that would later confound researchers: elevated ratios of carbon dioxide and carbon monoxide, anomalously high levels of nickel relative to iron, and an oxidized chemical balance unseen in typical comets. These early spectral hints suggested that 3IATLAS did not share the chemical fingerprint of solar system bodies. It had been built somewhere else, somewhere cold, distant, and unaltered by the solar-driven cycles familiar to planetary scientists. In the days following its identification, astronomers refined its orbit using every fresh measurement. Predictions emerged for its perihelion passage estimated at late October. Its closest approach to Earth, safe yet symbolically gripping, was placed in mid-December. It would thread through the inner solar system only once before disappearing again, thrown outward by the sun's gravity to resume its timeless voyage. Yet even as calculations mapped its path, a subtler story unfolded at the threshold of its discovery: the realization that its composition held clues not only to its origin, but to the environments that shape matter beyond our solar system. The early spectra hinted at molecules not merely frozen in place, but actively reshaping themselves as the object warmed. The first glimmers of sublimation, faint and tentative, signaled chemical processes that would soon intensify into phenomena no cometary scientist had witnessed so dramatically. As researchers debated the nature of its unusual ratios, why carbon dioxide appeared so prominent, why water emission was present at distances where water should remain locked in ice, they returned to the core mystery of the object's provenance. If it had formed outside any known protoplanetary disk, then its chemistry might preserve conditions present in the galaxy long before the sun ignited. Mineralogists compared its spectral patterns to those of carbonaceous chondrites, particularly the rare Cr class, whose metallic grains and organic richness hinted at formation in cold, chemically diverse environments. Planetary scientists noted that its oxidized volatiles resembled materials subjected to liquid water corrosion, a process that demanded heat sources it could not have encountered in the solar system's frigid outskirts. What then had shaped it? A newborn star, a tidal disruption in its birthplace, residual heat from radioactive decay, or interactions with shock waves in interstellar clouds? These questions simmered beneath the flood of data. At the same time, the astronomical community recognized that they were witnessing something that occurred perhaps once in a generation, a pristine ancient object transitioning from deep space dormancy into solar-energized awakening. Back on Earth, the public remained mostly unaware of its presence. News cycles barely shifted. Yet among researchers, excitement grew. Each night, as Earth's rotation brought new telescopes into position, the faint point of a light crept closer and brightened incrementally. The object's coma expanded. Early models predicted that as it neared 2.5 astronomical units, significant changes might occur, changes associated with water ice activation. Few predicted how dramatic those changes would be. But in these opening days, in the period when 3IATLAS was still just a new designation in survey logs, the mystery took root. The discovery phase became the foundation on which every later question would rise. What was this object? How had it survived so long in interstellar exile? And what hidden structures or materials lay dormant beneath its irradiated crust, waiting for the slightest touch of sunlight to stir them awake? Its approach to the sun would soon reveal answers that no scientist anticipated when the first faint observations were logged. For now, though, the world stood at the threshold of a story still forming. It was the quiet before a transformation that would unfold in the weeks ahead, revealing an object whose behaviour defied classification and whose chemistry whispered of places older and stranger than the solar system itself. As the object drifted inward from the dark perimeter of the heliosphere, the first spectroscopic measurements arrived not with fanfare, but with the calm, methodical certainty of scientific ritual. Observatories across the world began to dissect the faint light, escaping from its coma, filtering it into wavelengths that revealed the hidden fingerprints of its chemistry. What emerged was not just unusual, it was unprecedented. In the earliest exposures, researchers expected the signature of water vapour to dominate once the object warmed. Instead, something else rose sharply from the spectral lines, carbon dioxide, bright and assertive, overwhelming the familiar emissions of water by a factor of nearly 8. In the context of solar system comets, such a ratio was extraordinary. It stood 4.5 standard deviations beyond the expected range, marking the object as a total outlier in volatile composition. Accompanying this CO2 abundance was an equally surprising surge of carbon monoxide, about 1.65 times greater than the water emission. Both ratios suggested a degree of oxidation rarely seen in native comets. They hinted at a surface shaped not by repeated passages near a star, but by processes that unfolded in a far different environment. But even more striking was the detection of nickel in the object's coma. Nickel is not an unusual element in the cosmos. Earth itself contains vast amounts locked within its core. Yet the nickel-to-iron ratio here was elevated far beyond expectations. The presence of nickel floating freely among the vaporized materials suggested that the surface, or perhaps even the internal structure, had undergone processes that unlocked metals typically bound tightly in stony matrices. This anomaly mirrored a peculiar trait of CR carbonaceous chondrites, rare meteorites thought to have formed well outside the solar nebula in cold, chemically dynamic regions where metal grains interacted with water or other volatiles. Such a resemblance raised immediate questions. Was 3IATLAS the fragment of a planetesimal formed in another stellar nursery? Did it originate from a zone where icy grains mingled with metals under conditions unlike those in our own protoplanetary disk? The spectral data offered no direct answer, but every wavelength of light seemed to whisper that this object carried the imprint of a formative process unfamiliar to human experience. Then came the colour measurements. Telescopes reported a deep muted red surface, an optical characteristic reminiscent of trans-Neptunian objects that had spent billions of years beyond the sun's warmth. This coloration often arises from long-term exposure to cosmic radiation, which rearranges surface organics into heavy tar-like compounds. For 3IATLAS, the implication was clear: it had been sculpted by the harshness of interstellar space, for a timescale so vast that even the galaxy's slow drift of stars could not easily account for its solitude. Another anomaly emerged when researchers examined the object's brightness curve. Typical comets behave predictably. They brighten gradually as they warm with sporadic outbursts when patches of volatile ices erupt. But 3IATLAS followed no such script. Before any major activation, its light curve hinted at an unusually cohesive surface. There were none of the chaotic irregularities that plague many comets, no sudden flickers, no rotational asymmetries. Instead, it behaved with a stable, almost serene consistency, as though its outer layers had been compressed and aged into a unified structure. This stability made what followed even more confounding. At around 2.5 astronomical units, when the sun's heat touched its surface with just enough intensity, the object underwent a transformation so sudden and dramatic that astronomers questioned their own data. A 2-magnitude jump in brightness erupted across a span of days. Such an event should have signalled a localized outburst, perhaps a vent opening a pressurized pocket of gas escaping. But the surge did not subside. It persisted. It grew. And as more images arrived, it became clear that the brightening was not the signature of a single eruption, but of an entire surface awakening simultaneously. Before scientists could interpret this activation, more anomalies surfaced. One was the detection of oxygen emission at distances where such a signal should not exist. Oxygen typically appears when water ice sublimates, yet at over 2.5 AU water should have remained locked in solid form resistant to the modest warmth. Its presence implied that the object's outermost layers had stored volatile compounds not simply as pristine ice, but as chemically bound mixtures shaped by long-term cosmic ray exposure. The interstellar environment appears to have implanted oxidants deep into the object's surface, gradually building a reservoir of materials that could release oxygen under the right conditions. Such processes are not speculative. Laboratory studies of irradiated ices reveal that cosmic rays can generate complex molecular networks, splitting water into hydrogen and oxygen, and producing chains of organic compounds. Over billions of years, these reactions can create stratified layers rich in volatiles and prebiotic chemistry. 3IATLAS seemed to embody that history. Its spectrum was the signature of a body that had never been warmed enough to melt or restructure these irradiated layers until now. The anomalies collected into a growing list, a volatile inventory unlike any known solar system comet. Elevated nickel levels pointing toward ancient metal-rich origins. A reddish, radiation-processed surface marking eons in deep space. Oxygen emission at unexpected distances. A brightness behavior resistant to conventional cometry models. All these signs converge toward a singular idea. 3IATLAS was not merely unusual. It was fundamentally foreign in composition, a relic of processes that unfolded far from any star humans had studied. Yet the more the object revealed of its chemistry, the more the underlying mystery deepened. Its oxidized volatiles suggested it had interacted with liquid water, yet it should never have been near a heat source. Its metals hinted at hydrothermal alteration, yet no thermal events were known to occur in the void between stars. Its surface organics resembled those found on outer solar system bodies, yet its trajectory traced no path through their ranks. What then had shaped this wandering fragment? Where had it acquired its chemistry? Which forgotten star had birthed it? And why did it still contain such an abundance of intact volatiles after millions of years exposed to cosmic radiation? These anomalies were the first cracks in the facade of the mystery. They foreshadowed even stranger behavior yet to come, behavior that would force scientists to reconsider everything they assumed about objects formed beyond our solar system, and perhaps even the very mechanisms by which chemistry evolves across the galaxy. The deeper the measurements went, the clearer it became that 3IATLAS was not simply an interstellar visitor. It was a museum of ancient processes, a carrier of molecular stories written long before Earth formed an object whose anomalies were not mere curiosities but the opening notes of a deeper unresolved question about the nature of life's ingredients and their voyage across the stars. By the time 3IATLAS reached a distance of 2.5 astronomical units from the Sun, a place still colder than the outer edge of Mars' orbit, something began to stir beneath its irradiated crust. It happened quietly at first, a faint rise in luminosity, captured only in the precision of photometric curves. But then as hours turned into days, the change accelerated. The object brightened by 2 full magnitudes. In astronomical terms, this was an eruption of light, the equivalent of a sleeping mountain suddenly exhaling a plume that could be seen across continents. Yet this awakening did not behave like the typical outburst of a cometary jet. Outbursts fade, they spike and collapse. They leave behind a lingering brightness that gradually returns to baseline. But the brightness of 3IATLAS did not return. It stabilized at its new level. Then slowly it continued to rise. This anomaly forced observers to confront an unexpected possibility. The entire surface of the interstellar object may have crossed a thermal threshold simultaneously. A global change, not a local eruption. A worldwide activation of embedded volatiles in a body untouched by starlight for millions, perhaps billions of years. The idea was unsettling. Comets born in our solar system often carry a thin mantle of processed material on their surfaces, dust resinous organics layers formed by many previous passes around the Sun. Beneath that thin crust lies frozen water, carbon monoxide ices, and more volatile compounds waiting for warmth. But such objects awaken gradually. A patch here, a localized vent there. The rotation of the comet exposes sections unevenly, generating sporadic jets that vary depending on orientation and solar angle. 3IATLAS, however, rotated every 16 hours, a rapid spin for a body possibly up to several kilometers across. This rotation ensured that solar heating was distributed evenly across its exterior. No single region experienced prolonged heating. No particular patch baked while another froze. Thus, when the object crossed the thermal line at which water ice begins to sublimate more rapidly around 2.5 AU, the warming effect spread like a soft wave across the entire surface. This homogeneity of heating allowed for something that almost no solar system comet exhibits: a global cryovolcanic surge. Cryovolcanism in such a context does not resemble lava flows or molten rock. Instead, it is an eruption of ice's water, carbon dioxide and carbon monoxide, suddenly transitioning from solid to gas. For an interstellar object like 3IATLAS, this process was amplified by the fragile nature of its crust. Over its incomprehensibly long journey through the interstellar medium, it had accumulated layers of frozen volatiles mixed with organic-rich dust. Cosmic rays had etched their mark into every surface particle, splitting molecules, forming oxidized compounds and embedding pockets of reactive materials. When sunlight touched these layers, the stored energy of millions of years met the gentle rise of solar heat. The effect was catalytic. Water ices began to sublimate not gradually but explosively across the entire surface. As they vaporized, they released oxygen previously formed by cosmic ray dissociation and liberated trapped gases. Pressure surged beneath the brittle regolith, fracturing it. Underneath, water interacting with metallic grains, especially nickel and iron-rich fragments, facilitated Fischer-Tropsch-type reactions that produced carbon-rich molecules. All of this chemistry began to cascade outward just as the brightening was observed. Astronomers watched the sudden increase in luminosity with a mixture of awe and confusion. The timing was too precise, the activation too broad. Something transformative had occurred, and the brightness curve recorded it as a single sweeping motion upward. Soon telescopes confirmed what the light had hinted: the coma expanded dramatically. Jets that once seemed modest now stretched outward like the filaments of a living organism, awakening from a long hibernation. The coma thickened with water vapor, carbon dioxide and carbon monoxide, and the dust content increased in tandem. What had slumbered beneath the interstellar crust was now erupting into space with renewed vigor. But another surprise awaited. The composition of the material released during this surge mirrored the anomalies detected before: unusually high carbon dioxide relative to water, coupled with elevated carbon monoxide. These ratios, now released in real time, confirmed that the chemical oddities were not the remnants of an ancient epoch, but were actively shaping the object's current behavior. The brightness event at 2.5 AU became the central pivot in understanding 3IATLAS. It marked the moment when dormant chemistry awoke. It signaled the threshold between a body governed by the slow physics of interstellar cold and one driven by the energetic processes of the inner solar system. Observers realized that the object was far more volatile-rich than expected. Its surface, crusted with interstellar residues, was thinner than anticipated. Its internal ices were fresher, more pristine, unprocessed by any close past to a star in geological time. The lack of prior solar encounters was critical. Most comets that graze the Sun multiple times lose their volatile richness. Their surfaces harden over millennia, but 3IATLAS had no such history. It carried billions of years of accumulation organics formed in interstellar clouds, ices laid down in distant nebulae, mineral structures preserved in freezing conditions, where time moved slowly and energy rarely intruded. Thus, when the Sun finally touched it, the reaction was not gentle, it was transformative. The activation also revealed something else: the internal structure must have been porous but cohesive enough to retain its volatile load. If it had been loosely bound rubble, it might have fragmented during such a massive release of energy. Instead, it held together, suggesting a nucleus that blended ancient rock, metal, ice and organics into a solid matrix robust enough to withstand the awakening. The global nature of the event implied that the object's cryovolcanism did not originate from a single vent or fissure. Instead, pressure increased nearly everywhere at once. Large sections of surface likely cracked simultaneously. Jets erupted across broad swaths. Dust plumes rose. Water vapor swelled. Every new observation supported this interpretation, and as the coma expanded, something subtle but crucial occurred. The beginning of magnetite formation became more apparent in spectral signatures. This mineral iron oxide Fe2O4 arises during catalytic reactions involving liquid water and metallic grains. Its appearance suggested that transient liquid phases might have formed briefly beneath the surface during activation. In the vacuum of space, such liquid water exists only momentarily, but in those fleeting instants, chemistry accelerates. Magnetite, once formed, contributes not only to mineral layers, but potentially to magnetic behavior. Thus, the brightness surge hinted at more than cryovolcanism. It may have marked the onset of endogenous magnetism forming within the object. The crossing of 2.5 AU was the key that unlocked the chemical memory of a body older than the planetary systems now circling the Sun. It awoke, reacted, restructured, and revealed itself. Scientists watching it realized they were not witnessing a passing rock, but a transformation, a shift from deep time dormancy into an active state sculpted by the Sun's radiance. The awakening of 3IATLAS was not merely a moment in its journey. It was the moment that allowed Earth to glimpse its interior history, its chemistry, and perhaps the first hints of its deeper significance, that something ancient, volatile, rich, and reactive was passing through the inner solar system, carrying with it a potential narrative about how the building blocks of life travel between stars. As 3IATLAS sailed inward after its great awakening, its surface no longer resembled the quiet, inert shell it had worn for millions of years. The Sun began to sculpt it hour by hour, drawing out buried volatiles, loosening ancient grains, and igniting chemical processes that had slept since its origin in a distant stellar nursery. What emerged from this transformation was not a simple cometary form, but a living tableau of shifting jets, braided filaments, and volatile-rich structures, weaving outward into the void like threads pulled from an ancient tapestry. The first images revealing these changes arrived from ground-based telescopes in early November. Against the quiet blackness of space, the interstellar object displayed jets extending tens of thousands of kilometers, some straight and precise like needles of vapor, others twisting subtly with a wavering motion, reminiscent of plasma filaments reacting to invisible magnetic forces. In photographs taken night after night, the structures shifted not randomly, but with a distinct imprint of dynamics that were neither purely gas-driven nor purely dust-driven. Something more intricate was unfolding. Amateur astronomers accustomed to the familiar morphology of long-period comets were among the first to remark on the strangeness. Most comets exhibit a discernible primary tail flowing away from the Sun, with a fainter, straighter Aon tail occasionally trailing behind. Yet 3IATLAS developed additional structures that diverged from expectation. Jets rose not only from its night side, but from sectors where solar heating alone could not fully account for the intensity. Their distribution implied internal pressure and rotation working in concert with a rapidly evolving surface. The rapid 16-hour rotation of the nucleus played an important role in shaping these structures. It exposed new fissures to sunlight, with each turn energizing pockets of material beneath the crust. As sunlight reached them, gases burst outward in narrow columns, dragging dust grains with them. But these columns wavered in ways that suggested more than rotation-induced sweeping. Some filaments bent and twisted as though shaped by a magnetic influence, behaviors reminiscent of plasma interactions observed in cometary environments during missions such as Rosetta. Indeed, within each jet, electric and magnetic interactions may have danced between ionized particles and the solar wind. The object's coma, thick with ions, could act as a conductor, subtly altering the paths of emerging jets. Observers noted faint oscillations along their lengths, disturbances that propagated like waves along tensioned strings. These were not the chaotic trails of dust alone. They were structures suspended within an interplay of gas-plasma rotation and magnetic fields that had only recently awakened. Some of the jets appeared to originate from fractures formed during the global cryovolcanic surge at 2.5 AU. As 3IATLAS warmed, the expansion of sublimating volatiles pried open seams that had been sealed since before the Sun existed. The interstellar matrix of ices and organics fractured in multiple directions, creating vents across the surface. When these vents faced sunlight during rotation, they erupted. When they turned into shadow, they relaxed, cooling rapidly in the cold vacuum. This cycle produced pulsed behavior in the jet's intermittent intensification that aligned with the object's rotation period. The coma, once faint and undistinguished, became more structured. Dust released from the surface mingled with vaporizing molecules, creating a layered atmosphere that expanded outward into space. Embedded within this hazy envelope, astronomers detected wave-like patterns, ripples of brightness and shadow, as if the coma itself were breathing. Such structures often arise from interactions between gas pressure and solar radiation, but the scale and persistence of these waves suggested an additional agent, possibly the formation of magnetite grains, and the onset of weak magnetic ordering within the dust. As magnetite formed on the nucleus iron oxide born from catalytic processes between water, nickel and iron, the grains could become aligned by the object's magnetic field or by the external influence of the solar magnetic environment. Dust jets mixed with magnetite had the potential to create filaments that responded to magnetic stress. This idea, speculative but grounded in known mineral physics, offered one explanation for the unusual shapes photographed, but nothing was as surprising as the presence of multiple well-defined jets erupting after perihelion. Cometary activity often diminishes following a close approach to the Sun as volatiles are depleted. Yet 3IATLAS seemed to enter a heightened state of transformation. Jets lengthened, their intensity increased. Some extended beyond 50,000 kilometers, a scale rarely witnessed in detail. The nucleus appeared to be shedding material not chaotically, but through consistent, repeatable channels, as though internal reservoirs were being exposed layer by layer. These jets also varied in composition. Spectroscopy revealed shifting balances of water vapor carbon dioxide and carbon monoxide. This variability pointed to stratified layers within the nucleus' ancient deposits, laid down during eras separated by billions of years, each containing a distinct chemical legacy from cosmic ray processing, nebular accretion, or interstellar encounters. As each layer reached sublimation temperatures, its unique signature appeared in the jets. Another striking feature emerged: the apparent independence of these structures from gravitational influence. Traditional cometary jets disperse rapidly under solar radiation pressure, but some of the jets on 3IATLAS retained coherence over long distances, suggesting a stronger than expected binding force within the ejected particles. Again, this hinted at the possibility that magnetically susceptible grains played a role tethered by plasma currents or magnetic alignment. Even more curious were the filamentary plumes observed in late November. These plumes resembled braided strands, each thread twisting subtly around others. Such braiding, though delicate, is a known phenomenon in plasma physics, especially in environments where charged particles follow magnetic field lines while being pushed by solar wind. These braided plumes in the coma invited comparisons to solar prominences on vastly smaller scales, though the underlying physics would be simpler and colder. The surface of 3IATLAS itself, though never directly imaged, was inferred to be undergoing continuous restructuring. As jets erupted, they excavated pits and trenches. Dust mantles collapsed, new fissures opened. The subsurface layers once locked away beneath cosmic sediments were thrust outward, revealing more of the object's internal composition with each passing rotation. The interplay between sunlight and internal volatiles created a patchwork of rapidly changing terrain, an evolving geology visible only indirectly through the morphology of its emissions. By December, the entire object appeared transformed from what it had been upon discovery. It was no longer the quiet wanderer drifting into the heliosphere. It had become an active, breathing body responding dramatically to its first close encounter with a star in millions of years. The jets, the filaments, the waves, and the strange coherence of its plume structures all suggested that 3IATLAS was not simply shedding material. It was revealing its inner architecture, its long interstellar history, and the physical laws that had shaped it far from the Sun's domain. These emergent behaviors were only the beginning of what would soon become even more perplexing. As the object drew closer to perihelion, its transformations intensified, and one anomaly rose to the forefront, a tail that should not exist shining brightly in the direction of the Sun itself. As 3IATLAS swung past perihelion and began its outward climb, astronomers expected a familiar story to unfold. Comets brighten dramatically before their closest approach to the Sun, then fade as their volatiles diminish and solar energy weakens. Their anti-sunward dust tails shorten their ion tails thin, and the jets that once carved luminous arcs into space fall into silence. Yet in the case of this interstellar wanderer, only part of that script came to pass. Its main tail began to diminish. Yes, its brightness softened, its contours blurred, but something else emerged in its place. Something that grew brighter as everything else dimmed. Something that pointed impossibly toward the Sun. This sunward-facing tail, first hinted at in November, soon became the most perplexing structure of the entire apparition. Conventional comet physics dictated that such a feature should not exist. Dust tails are pushed away from the Sun by radiation pressure. Ion tails are swept outward by the solar wind. Both processes generate structures that invariably point away from the source of heat. But here a luminous plume of dust and gas stretched toward the Sun not as a faint anomaly or transient arc, but as a strengthening, increasingly defined structure. Every new observation showed it growing sharper, brighter, longer. It defied expectation. At first, some observers suspected an illusion. Projection effects can sometimes rearrange the apparent geometry of faint cometary structures. But as days passed and more telescopes turned toward the object, the reality became undeniable. This was a genuine sunward extending plume, persistent, expanding and evolving in concert with the object's rotation and continued sublimation. The puzzle deepened when set against the backdrop of the object's diminishing anti-sunward tail. After perihelion as 3IATLAS moved farther from the intense heat of the sun, its main dust tail began to fade. Jets that once stretched tens of thousands of kilometers contracted. The coma thinned, yet the sunward-facing structure, rather than shrinking, intensified. It extended further each night, brightening at a time when the object should have been losing the luminous energy that sustained such features. This oddity demanded explanation, but none of the traditional mechanisms fit. Radiation pressure could not push dust toward the sun. It acts outward. The solar wind could not sculpt such a structure. Its direction and vector oppose sunward motion. Even rare circumstances such as ripples or discontinuities in the solar wind could not stabilize a persistent tail pointing inward. Something else was governing the motion of the particles. The first clue came from the composition of the emitted dust. If the sunward tail was composed primarily of high-density mineral grains, magnetite for example, radiation pressure might act only weakly upon them. Such grains are heavy relative to their surface area, allowing gravitational influences to play a greater role than outward radiation forces. If the surface of 3IATLAS was producing an abundance of magnetite, as spectral readings suggested, those grains could linger near the nucleus long enough for other forces to shape them. But magnetite alone could not push a tail sunward. A second factor was needed. That factor may have been magnetism. As the object's catalytic chemistry produced magnetite across its surface, a growing population of magnetic grains could interact with any magnetic fields in their environment. At the same time, the comet's coma had been observed developing strong plasma characteristics, wave-like filament-structured jets and large-scale oscillations, consistent with the electromagnetic interactions. A cometary coma, especially a highly active one, can generate an induced magnetosphere formed by interactions between ionized gases and the solar wind. Missions to other comets have recorded magnetic fields strengthening significantly during solar storms at times, rising to hundreds of nanoteslas. If 3IATLAS possessed a robust plasma-driven magnetic environment, charged dust and magnetic grains might not behave in the typical dust-tail manner. Instead, they could become trapped or redirected by magnetic loops or pressure gradients, creating arcs or plumes that defy conventional expectations. A sunward tail could form if magnetic forces funneled grains toward regions of lower plasma pressure regions that counterintuitively might exist sunward of the nucleus during periods of unusual solar wind interaction. If the object encountered a localized solar wind disturbance, or if its plasma boundary behaved asymmetrically, a pocket of low pressure might persist between the object and the sun. Dust and ions could then drift inward rather than outward. Another possibility involved backscattering. If grains were heavy enough to resist radiation and were emitted from the night side of the nucleus as it rotated, they could travel in trajectories that gave the illusion of pointing sunward. But this explanation faltered when confronted with the persistence and growth of the structure. Projection illusions do not strengthen with time, they dissipate as geometry changes. Thus magnetism remained the only compelling pathway. If magnetite grains were aligning along magnetic field lines, and if those field lines were shaped by the unique plasma bubble of the object, in combination with the solar environment, they could create a plume-oriented sunward. The persistence of the tail could then be explained by a steady flow of such grains along stable magnetic channels. Yet even this model hinted at deeper complexities. To maintain a sunward structure of increasing brightness, the object would need not only a source of magnetic particles, but a regional magnetic asymmetry, robust enough to counteract solar radiation. Such asymmetry could arise from the object's internal magnetite distribution variations in its plasma sheath, or even the arrival of solar storms events known to intensify cometary magnetic fields dramatically. Observers found that the sunward plume grew most rapidly after perihelion, during a period of heightened solar activity, when storms erupted from sunspots aligned with the object's direction of travel. The coincidence was striking. As solar disturbances increased, the anti-sunward tail weakened while the sunward plume strengthened. This inverse relationship suggested that the solar wind was compressing one side of the coma while expanding the other, reshaping the plasma environment surrounding the nucleus in unexpected ways. The result was a reversal of visible structure. To researchers, it was a moment of deep uncertainty, one that challenged long-held assumptions about cometary dynamics. If an interstellar object with unusual chemistry could produce such a tail, then the physics of dust and plasma around comets might hold more variability than previously understood. The Sunward plume of 3IATLAS became the defining symbol of its strangeness, the signature that separated it from both Oumuamua and Comet Borisov. It suggested not merely a foreign origin, but an entirely different evolutionary path, one shaped by eons, in environments where magnetic forces, cosmic rays, and chemical evolution combined into a history our solar system has never witnessed. This anomaly did more than captivate observers. It deepened the central mystery. For if the sunward tail could exist, if the object could forge magnetite and complex organics while drifting between stars, and if its plasma behavior defied familiar patterns, then what else might be hidden within its evolving structure? Ahead lay theories involving catalytic chemistry, the origins of life's building blocks, and the possibility that objects like 3IATLAS serve as carriers of molecular heritage across the galaxy. But before those ideas could be explored, the scientific world had to confront a more immediate revelation that the object's behavior was not just unexpected, it was transformative. It signaled that 3IATLAS was rewriting in real time our understanding of how interstellar objects interact with the Sun. And it was only beginning. Long before 3IATLAS ever approached the Sun, long before its jets awakened or its volatile, rich crust fractured into luminous plumes, the clues to its deeper nature lay hidden in the patterns of its spectra. As astronomers pored over those signatures, they found themselves returning again and again to a curious resemblance. The chemical fingerprint of this interstellar wanderer echoed the rarest meteorites known on Earth, the CR carbonaceous chondrites. These fragments trace their origin not to the inner solar system nor to the warm regions where rocky planets arise, but to cold, distant environments where star formation begins in whispers rather than flames. What set the CR chondrites apart was their composition. They contained high levels of organic material, volatile compounds, and a distinctive ratio of nickel to iron traits that became unexpectedly relevant when 3IATLAS announced itself with spectral lines rich in CoCO2 and nickel. As researchers compared the readings, a pattern emerged. This was not the chemistry of a comet born from our solar nebula. It bore the imprint of a world assembled beyond it, perhaps in a region where metal grains and ices mingled unaltered by starlight. These meteorites, found only rarely in collections on Earth, had long posed their own mystery. Their mineral assemblages, magnetite clusters, hydrated silicates, nickel-iron beads suggested interaction with liquid water. But the environments in which they formed were unclear. They appeared too pristine to have experienced significant heating, too volatile rich to have originated near a star, too chemically processed to be mere fragments of raw interstellar dust. Now the chemistry of 3IATLAS illuminated those same contradictions. In its oxidized volatiles, its high CO2 to water ratio, its elevated nickel presence, and its continuous release of magnetite-forming material, astronomers saw the same interstellar fingerprints that the CR chondrites had carried for billions of years. These were not the traits of a rocky object shaped by repeated passages into a solar wind, but those of a body that had formed beyond the crowded radius of any early protoplanetary disk, assembled instead from residual materials drifting at the periphery of a young star's influence. The process begins, as scientists believe, in the diffuse halo around forming stars, a region where particles accrete not in the intense heat of the inner nebula, but in the quiet cold of the outer envelope. Temperatures there remain low, water exists as ice, iron and nickel condense into grains that are not 1,000 Diaz droplets, but frigid metallic seeds. Cosmic rays penetrate these regions, easily catalyzing subtle chemistry over millions of years. What forms in these conditions are objects that do not resemble the carbonaceous bodies of our solar system, but preserve signatures of pre-stellar material dust and ice that predate even the ignition of the parent star. If 3IATLAS emerged from such a place, its chemistry would reflect that history. It would contain abundant ices embedded with metals capable of catalyzing organic synthesis. It would carry volatiles that had never been heated enough to sublime until now. Its ratio of carbon dioxide to water would be influenced not by solar radiation cycles, but by pre-solar oxidation conditions. Its nickel-to-iron balance would match the Cr-type chondrites rare on Earth, but remnants of the earliest planetary building materials. The Cr chondrites, like the one famously recovered in Italy, also bear an unusual abundance of organics, amino acids, hydrocarbons and molecules, with structures suggestive of prebiotic potential. Some contain water in mineral form. Many contain magnetite small grains that form when iron interacts with water under specific conditions. The discovery that 3IATLAS was producing magnetite as it approached the Sun recalled these same meteorites almost perfectly, but 3IATLAS was not merely similar, it was richer in volatiles, richer in oxidized compounds, richer in nickel. This implied a more extended or more intense history of cosmic ray processing, the slow, relentless bombardment that transforms simple ices into complex organics over deep time. If Cr chondrites were fragments of bodies that formed just beyond the early solar nebula, then objects like 3IATLAS might be fragments of bodies that formed even farther outward, or in entirely different stellar systems, places where conditions favoured the accumulation of organic precursors in extraordinary abundance. The object's estimated age ranging from 3 to 11 billion years pushed this idea further still. If accurate, 3IATLAS was older than the solar system itself. It may have crystallized in the debris field of an earlier generation of stars carried outward by gravitational interactions into the interstellar medium long before our Sun ignited. Over the ages, it would have encountered shock waves from dying stars collecting new layers of dust and molecules. It might have drifted through the wake of supernovae or cold molecular clouds. Each encounter added complexity to its chemistry. Each eon reshaped its structure without the erasing influence of solar heat. Cr chondrites form magnetite through a process known as aqueous alteration, a reaction that requires transient liquid water. The prospect of liquid water forming inside 3IATLAS at any point in its long interstellar life may seem improbable. Yet as the Sun's heat awakened the body, the catalytic interaction between metal grains and water ice generated liquid microfilms, fleeting ephemeral pockets, where chemistry accelerated dramatically. These microreactions, though short-lived, had consequences observable millions of kilometers away: magnetite forming volatiles, oxidizing and organic molecules synthesizing. But here the interstellar object surpasses its chondritic cousins. While Cr chondrites preserve the mineral record of those processes, 3IATLAS arrived not as a fossil, but as an active system. Its reaction chemistry was unfolding in real time. As observers measured its evolving emissions, they watched the same reactions that shaped early planetary material, but now animated by sunlight after ages of dormancy. A profound implication took root. If Cr chondrites represent fragments of ancient planetesimals from our early solar system, and 3IATLAS resembles them so strongly while being older and chemically richer, then this object may be a sample not of our own origins, but of the galaxy's primordial chemistry. A relic from early star formation cycles, a messenger carrying chemical history from a time when the Milky Way was young and life had not yet emerged on Earth. It suggests that the organic inventory of the universe, the capacity for molecules to assemble into sugars, amino acids and nucleobases, was not confined to one star system. It existed across many, seeded by processes that operated wherever metal ice and cosmic radiation coexisted in cold, slow-moving environments. And so 3IATLAS stands as a bridge, a link between the rare meteorites found on Earth and the ancient chemistry of worlds long extinguished. It carries within its core the signature of a formation environment that predates the solar system and echoes the same mineralogical voice we hear in Cr chondrites. Yet unlike those meteorites, it remains whole. It remains alive in its reactions. It remains capable of transformation. In its resemblance to these rare meteoritic fragments and in the ways it exceeds them, 3IATLAS offers a glimpse into the prehistory of planets, the materials that seeded solar systems, and perhaps the molecular foundations upon which life arises. It connects our understanding of small bodies not only to our own Sun's past, but to the broader, older, and more mysterious history of the galaxy itself. And from this resemblance, from this ancient lineage of materials, grows an even deeper question. If 3IATLAS contains the same building blocks, and perhaps more than the meteorites that shaped early Earth, then what role might interstellar objects like it play in the spread of life's raw chemistry across cosmic distances? Ahead lies the hypothesis that such bodies may not merely resemble life's ingredients, they may carry them, refine them and deliver them from star to star, As the chemistry of 3IATLAS unfolded before the eyes of astronomers, one thread emerged with growing clarity, a thread woven through every emission line, every mineral signature, every plume of dust and gas rising from the object's awakening surface. Beneath the spectral anomalies and unusual volatiles lay a fundamental truth: this body was not merely rich in organics. It was actively producing them. The catalysts were embedded in its very structure. To understand the significance of this, one must imagine the interstellar object as a slow-moving crucible drifting through the galaxy. For billions of years, 3IATLAS wandered beyond the influence of any star, exposed only to the faint glow of starlight and the constant rain of cosmic rays. These high-energy particles, protons, heavy nuclei and ionizing radiation, penetrated the surface, splitting molecular bonds, rearranging atoms and embedding oxidants into icy matrices. Over unimaginable spans of time, the cosmic ray processing created stratified layers, enriched with radicals, peroxides, carbon chains, and molecular fragments, waiting for heat to unlock their reactions. Such chemistry lay dormant through its journey. But when the sun's warmth reached the object for the first time in at least 10 million years, something remarkable occurred. The interstellar chemistry that had been preserved in slow motion began to accelerate. And in that acceleration, astronomers glimpsed the same pathways that may have shaped the earliest building blocks of life in the galaxy. Central to these pathways were two metals, iron and nickel. Both were present in elevated ratios within 3IATLAS, and their roles in catalytic reactions are profound. On Earth, nickel-iron catalysts are used in industrial processes to convert carbon monoxide and hydrogen into hydrocarbons. In the cold environments of interstellar space, similar reactions unfold at far slower rates, but they do unfold. When mixed with water ice and carbon-rich molecules, nickel and iron grains act as natural catalysts, driving Fischer-Tropsch-type reactions that produce organic compounds including simple amino acids, long-chain hydrocarbons and sugars. Upon warming, the reaction rates increase dramatically. In the case of 3IATLAS, the catalytic environment appears ideal. Its high nickel-to-iron ratio, strikingly reminiscent of Cr carbonaceous chondrites, suggests a surface and interior abundant in catalytic metallic grains. When water ice sublimated around 2.5 AU, and oxygen was released from irradiated layers, the metals were exposed to liquid microfilms of water for brief but crucial moments. During these transient phases, reaction rates would have surged, transforming carbon monoxide and hydrogen into hydrocarbons and oxygenates, and indeed the spectral signatures matched this behavior. Elevated CO and CO2 levels the formation of magnetite Fe3O4, and the likely release of complex organics as dust and vapor. The formation of magnetite itself is a key indicator. On Earth, magnetite emerges when iron reacts with water under catalytic conditions, often at hydrothermal vents, where the building blocks of life may have first arisen. On 3IATLAS, magnetite likely formed through similar reactions, albeit on microscopic scales where cosmic rays pre-energized the chemistry, and solar heating supplied the final activation energy. With magnetite comes the ability to align magnetic fields, and thus the object's surface gradually built up a population of magnetic grains, capable of interacting with plasma-influencing dust trajectories, and perhaps even shaping the peculiar sunward-facing tail. But magnetite is only half the story. The other half lies in the organics that form alongside it. When water ice breaks apart into hydrogen and oxygen under cosmic irradiation, and when carbon monoxide and carbon dioxide are present in abundance, as they are on 3IATLAS, the conditions become ripe for the synthesis of more complex organic molecules. Under catalytic influence, these reactions can produce amino acids, nucleobase precursors and simple sugars. Recent discoveries from the OSIRIS-REx mission to asteroid Bennu strengthened this interpretation dramatically. Bennu, a mere B-type asteroid less organic-rich than D-type bodies like 3IATLAS, was found to contain glucose, ribose uracil amino acids, and other essential prebiotic molecules. If Bennu, shaped by solar system processes and exposed repeatedly to the sun, retained such molecular richness, an interstellar object untouched by starlight for eons could harbour even more abundant and diverse organics. Moreover, D-type asteroids which resemble 3IATLAS spectrally are known to contain far higher levels of organics than Bennu. Their deep red coloration reflected in early observations of 3IATLAS arises from radiation-processed hydrocarbons. Such surfaces indicate long exposure to cosmic rays, but little thermal alteration, precisely the conditions under which prebiotic molecules accumulate without being destroyed. The catalytic processes unfolding on 3IATLAS thus suggest not only preservation, but active formation of life's building blocks. As the object warmed its internal chemistry, accelerated, releasing these molecules into space through jets, plumes, and the broadening coma. Some of these molecules may have existed for billions of years, preserved so perfectly in cold interstellar isolation that they predate Earth entirely. Others may have formed in recent weeks, catalyzed into existence by reactions that began the moment the sun's light touched their host. In either case, 3IATLAS functions as a natural reactor, turning cosmic dust and ice into organic complexity. And it does so on a scale that may be common across the galaxy. The very metals that form in supernovae iron and nickel are also the catalysts required for organic synthesis. The water that condenses in molecular clouds becomes the solvent. The carbon monoxide and carbon dioxide that permeate nebular environments become the reactants. And the cosmic rays that fill interstellar space provide the energy. The ingredients are universal. The reactions are inevitable. The molecules are ancient. If 3IATLAS carries organic synthesized across billions of years and multiple stellar environments, then it embodies the chemical continuity of the galaxy. Its structure is layered with the history of elements forged in stars that died long before the sun was born. Its chemistry speaks of processes that predate planets, oceans, atmospheres, and the emergence of biology. In this light, the interstellar object becomes more than a comet. It becomes a witness to the galaxy's natural tendency to form complex molecules. It carries frozen within its crust and now released through solar activation the products of reactions that blur the line between mineral chemistry and protobiology. This realization leads naturally, almost inevitably, to a deeper question. If the ingredients and pathways for building organic complexity are so embedded in objects like 3IATLAS, then could such bodies act as vectors for dispersing these molecules across cosmic distances? Could they seed star systems not just with dust and ice, but with the chemical scaffolding of life itself? The Interstellar Seed Hypothesis emerges here not from speculation, but from the convergence of observation chemistry and cosmic history. 3IATLAS, with its rich catalytic environment, its abundance of volatiles and its active organic synthesis, may be one of countless travelers distributing the building blocks of life across the galaxy. Whether by design or by nature, such objects carry forward the same story that life may not begin in isolation, but arise from a cosmic network of shared chemistry, exchanged through the slow drift of bodies like this one. As the chemistry of 3IATLAS revealed itself, its catalytic metals, its magnetite, its volatile reservoirs, its abundance of carbon-rich compounds, a single idea began to crystallize in the minds of astronomers and astrobiologists. Perhaps this object was not only a traveler through interstellar space, but also a carrier, not of life in the biological sense, but of the raw ingredients from which life can emerge. This idea, once whispered at the edges of speculation, took shape as the observational data accumulated. The Interstellar Seed Hypothesis, long a theoretical concept now found in 3IATLAS, a living example moved from abstraction into evidence. Panspermia, the notion that life or its precursors might spread across the galaxy via drifting celestial bodies, has existed in scientific discourse for over a century. Some versions propose the transport of actual microbes. Others more conservatively imagine that life's chemical foundations, amino acids, sugars, nuclear bases are dispersed by asteroids, comets, and dust grains into young planetary systems. For decades, the difficulty lay not in imagining such a process, but in identifying any object that carried the necessary chemistry intact across cosmic distances without being sterilized or erased by heat. 3IATLAS broke open that barrier. Here was a body that had wandered the galaxy for 10 million years since passing near any star. And before that, perhaps billions of years drifting through the cold interstellar medium. Its surface had preserved every imprint of that journey, cosmic ray processed, organics, irradiated ices, stratified residue layers, enriched with radicals and oxidized volatiles. More importantly, the object was not merely a container, it was a reactor. Under heat, it produced amino acid precursors, sugars, magnetite and hydrocarbons through natural catalytic processes. This meant that even if many of its organics had been destroyed by cosmic rays during its journey, new ones were being actively generated as it entered the sun's domain. Objects like this did not simply carry the molecular seeds of life, they manufactured them. This revelation transformed the Interstellar Seed Hypothesis from a distant possibility into a mechanism grounded in observable chemistry. If 3IATLAS formed around a star that may no longer exist, carried such a rich inventory of organics into our solar system, then how many millions of similar bodies may have passed through before the rise of Earth's earliest oceans? How many such carriers might have contributed materials that later assembled into RNA strands, metabolic structures, or early protocells? The OSIRIS-REx findings on asteroid Bennu further strengthened the connection. Bennu, a relatively ordinary B-type asteroid, was found to contain glucose, ribose, uracil, 50 types of amino acids, and multiple sugar alcohols. These discoveries demonstrated that even a thermally processed solar system-born asteroid could retain a suite of prebiotic molecules essential for life's chemistry. If Bennu, which had repeatedly drifted near the Sun, preserved such richness, then an interstellar object untouched by stellar heat for eons could preserve and produce even more. Thus 3IATLAS emerged as a possible exemplar of a much larger population. In the Milky Way, billions of rogue planetesimals drift between stars ejected during the violent early histories of solar systems. The majority remain forever unobserved, cold, solitary, and chemically rich. If even a fraction of them carry reactive metals and ices, their long cosmic journeys become opportunities for slow synthesis. Cosmic rays, far from being destructive alone, serve as creative agents, fragmenting molecules and generating radicals that later assemble into larger organic frameworks when warmed. When such bodies occasionally encounter a stellar system, the warming they experience can trigger rapid chemical activation. Jets erupt, ices melt into brief microfilms, volatile compounds reorganize, new molecules form, and are then released into space through outgassing and cryovolcanism. The result is the dispersal of prebiotic materials not only within the comet's own environment, but into the wider space it traverses. 3IATLAS demonstrated this vividly. The jets extending 50,000 kilometers from its surface were not merely dust and vapor, but carriers of complex organics. As the object approached the Sun, it shed molecular material across millions of kilometers of space, and as Earth passes through that region next spring, it will cross through the debris trail of this interstellar visitor, perhaps encountering dust grains containing chemical histories from beyond the solar system. Yet even more intriguing is the layered complexity of 3IATLAS's structure. The volatile rich crust likely formed over billions of years through accretion in the interstellar medium. Each layer irradiated, oxidized, chemically altered, preserved a different epoch of the object's journey. These layers are like geological strata on Earth, except that their timescales are not millions but billions of years. Each outburst, each jet, each plume released during its solar encounter expelled not merely dust but an archive of molecular evolution. Thus, the Interstellar Seed Hypothesis expands beyond the simple notion of transportation. It becomes a story of the galaxy's ability to refine and distribute chemical potential. Stars forge elements, supernovae send them outward, cosmic rays sculpt them, icy bodies accumulate and protect them, and when those bodies encounter warmth, they release them anew into places where planets may one day form. In this perspective, objects like 3IATLAS are the quiet architects of molecular diversity in the galaxy. Some scientists propose that such bodies may even serve as dynamic chemical incubators, producing different classes of molecules depending on environmental conditions. In cold regions, cosmic rays generate radicals and peroxides. In warmer regions, catalytic metals like nickel and iron drive hydrocarbon synthesis. If the object passes near a star as 3IATLAS has now done, transient liquid water phases provide additional reaction pathways, creating magnetite and complex organic compounds. A striking implication arises even without biology. Chemistry on such bodies can progress toward greater complexity over time. Each interstellar object becomes a tiny drifting laboratory. And because these bodies travel independently of any star system, their chemistry represents a broader galactic heritage, molecules synthesized from stellar debris long before the Sun was born and carried into regions where new stars and planets emerge. In this sense, 3IATLAS is not simply a visitor. It is a messenger of the galaxy's chemical memory. The Interstellar Seed Hypothesis suggests that early Earth may have received part of its molecular inventory not just from solar system comets and meteorites, but from ancient interstellar bodies similar to 3IATLAS. Their dust settling into Earth's primordial oceans could have delivered pieces of chemistry, refined across multiple generations of stars. If life emerged from such ingredients, and if these ingredients themselves originated from far older stellar systems, then humanity is connected chemically not only to the Sun, but to the broader history of the Milky Way. 3IATLAS is a rare opportunity to witness this mechanism in action. Its chemistry is active. Its jets are releasing materials forged in the interstellar medium. Its structure preserves the imprint of ancient worlds, and its very existence passing briefly through the solar system before continuing its endless drift suggests that life's building blocks do not belong to any one planet or star, they belong to the galaxy. From this vantage, the question deepens: if molecules can travel between stars so freely, if organic chemistry can survive the cold, and if catalytic reactions can occur in bodies like 3IATLAS, then perhaps life's emergence is not a solitary miracle, but a galactic inheritance shared across countless worlds. As 3IATLAS released its plumes of dust vapor organics and magnetite into space, another layer of its identity came into view, one far less visible than its jets, yet profoundly influential in shaping their behavior. Around the object, subtle fields began to form and shift, weaving an invisible cocoon of plasma and magnetism. These phenomena do not typically dominate the discussion of comets, yet for an interstellar body carrying a unique mineralogy, rich in nickel iron, and freshly formed magnetite, the magnetic environment could not be an afterthought. It might be one of the defining elements of its story. In the cold vacuum of interstellar space, any drifting body accumulates a thin veil of plasma around it, created by the interaction of cosmic rays with its surface ices and dust. But such a sheath is faint, silent, inert, doing little more than tracing an outline where charged particles occasionally gather. Only when a body approaches a star does that sheath awaken, and when 3IATLAS crossed into the Sun's domain, the solar wind began to shape its plasma environment in ways that revealed the object's hidden architecture. Ionized gases, carbon monoxide, carbon dioxide, water vapor streamed from its jets, forming a diffuse atmosphere around the nucleus. As ultraviolet light struck these molecules, they broke apart, releasing electrons and creating ions. These charged particles spread into space, interacting with the solar wind. That interaction formed what planetary scientists call an ionopause, a boundary, where the pressure of the solar wind meets the pressure of the comet's own ionized emissions. Around this boundary, electric currents flow. Magnetic fields are induced. Plasma waves form and ripple outward. This behavior is not theoretical. During the Rosetta mission to Comet 67P Churyumov-Gerasimenko, scientists observed the formation of a magnetic cavity around the nucleus, with field strengths fluctuating between 30 and 50 nanotesla, an impressive range for a small body. When solar storms struck the comet, the magnetic field intensified dramatically, reaching up to 300 nanotesla. These fields were not constant, but dynamic, folding and unfolding in complex patterns as plasma flowed around the comet's surface. Now, 3IATLAS exhibited similar but amplified behaviors. Its plasma environment, already unusual due to its volatile composition, became even more extraordinary as magnetite grains formed on the surface. Magnetite is not just a magnetic mineral, it is one of the strongest naturally occurring magnetic materials known. When produced in abundance and mixed with dust, grains lofted into space, magnetite gives the ejector the ability to respond not only to gravity and radiation pressure, but to magnetic fields as well. Dust laden with fine magnetite can align along magnetic field lines, twist into filaments, and remain coherent over long distances. Thus, the appearance of braided jets, wavering structures, and the astonishing sunward-facing tail suddenly acquired a possible physical context. The magnetic cocoon around 3IATLAS was guiding the motion of dust and ions in ways no ordinary comet could replicate. If the object's surface generated enough magnetite, and if its plasma sheath grew large enough, then magnetic tension and pressure gradients could sculpt arcs of dust that defy the expected directions. Solar wind particles compressing one side of the coma could create magnetic draping patterns, loops, or channels of field lines that guide dust inward or sideways. Grains might move along field lines as they do in solar prominences suspended against the outward push of radiation pressure. In essence, a comet with significant magnetic properties behaves not like a passive body-shedding dust, but like a miniature magnetosphere, a tiny temporary planet-like system with its own internal physics. The potential for magnetism grew even more intriguing when coupled with the object's rapidly forming magnetite. Laboratory studies reveal that magnetite grains can spontaneously align in external magnetic fields. On 3IATLAS, such alignment could occur within the ejecta as they left the surface. Clusters of aligned grains can create micromagnetic fields that interact not only with the comet's environment, but with each other, forming coherent filaments and oscillating waves, features observed in high-resolution images. Even more compelling is the possibility of charge separation. As dust jets erupt, heavier grains lag behind while lighter ions stream forward. This separation creates electric currents along the jets. Those currents in turn generate magnetic fields strong enough to shape the jets themselves. Plasma physicists have long documented such self-organizing behavior in laboratory discharges and astrophysical environments. Now 3IATLAS seem to be demonstrating it on a scale visible across millions of kilometers. The interstellar traveler was generating not just chemistry but physics, an intricate evolving interplay of ions, electrons, magnetic grains, and solar wind. An additional layer emerged when researchers considered the object's rotation. A 16-hour spin means that any magnetic fields induced within the body, either from alignment of magnetite or from moving charge particles, would rotate as well. This rotational modulation could create periodic distortions in the magnetic sheath, producing patterns of waves or spirals in the surrounding dust. Some jets indeed appeared to display a rhythmic curvature, bending gently as though tracing the motion of a massive slow-turning hand. The result was something unique among observed comets, a dynamically shifting magnetic cocoon shaping the morphology of its structures. Radiation pressure and gravity still played their roles, but magnetism, usually a subtle effect, had risen to the foreground. And as the object passed through regions of heightened solar activity, each solar storm became an opportunity for amplification. Intensified solar wind pressure compressed the plasma sheath. Shock fronts sent waves of charged particles crashing into the comet's coma. Magnetic boundaries rearranged, reoriented, and sometimes snapped into new configurations. Each such event could have reshaped the Sunward plumes, strengthened its brightness, or restructured the jets. All these interactions hinted at a deeper question. Could such a magnetic environment shield delicate molecules within the object's interior? Could magnetite formation, plasma boundaries, and induced fields provide protection against the mutating effects of the cosmic radiation? On Earth, magnetism plays a crucial role in preserving life by deflecting charged particles. In the interstellar medium, any shielding mechanism, no matter how small, could help preserve complex molecules for millions or billions of years. Thus, 3IATLAS's magnetic cocoon was not merely an aesthetic curiosity, it may have been a preservation mechanism, a stabilizing envelope allowing the object to carry prebiotic molecules across vast distances without destroying them. The traveller moved onward, wrapped in this shifting invisible architecture. Its magnetosphere, small, temporary but profoundly influential, was the unseen hand guiding dust, shaping jets, resisting radiation, and perhaps holding within it the seeds of chemistry older than the sun itself. In the interplay of plasma and magnetism around 3IATLAS, the scientific community glimpsed something rare: the possibility that interstellar objects possess their own internal systems, their own subtle forces that evolve during solar encounters. And with these forces comes an even greater question: how might such magnetic environments interact with the young forming systems they pass through? Might they influence the earliest chemistry of protoplanetary disks or seed regions with protected organic matter? The cocoon of 3IATLAS suggests that the galaxy's chemistry does not merely drift passively. It travels inside magnetic envelopes shaped by dust ice and metal carrying complexity across the interstellar sea. By late October 30, Atlas reached the defining moment of its journey through the inner solar system perihelion. On October 29th, the interstellar traveller passed its closest point to the Sun, a furnace of energy unlike anything it had encountered in at least 10 million years. After its long, silent drift through the galactic dark, the sudden rise in radiation was not simply a change in temperature. It was a transformation of state, an astronomical event capable of reshaping both the object and our understanding of it. In deep interstellar space, the object had lived in the faintest glow, a radiance of roughly 10⁷ to 10⁸ watts per square meter, scarcely more than the cold breath of starlight reflected off dust grains. At perihelion, that environment shifted to nearly 735 watts per square meter, a difference so monumental that no surface material could remain unchanged. Volatile ices responded first, sublimating at unprecedented rates. Beneath them, frozen layers accumulated over billions of years began to fracture. Dust rose into the coma in thick veils, and the chemical pathways seeded by cosmic rays throughout the object's long history suddenly fired into motion. The perihelion encounter was not a moment, it was a crucible. The sun became alchemist catalyst architect, reshaping chemistry and structure with every passing hour. The coma thickened explosively. Jets that had reached tens of thousands of kilometers before now extended even farther, blooming into vast curving pillars of dust and gas. Their shapes fluctuated not only with solar pressure, but with the internal state of the nucleus. Each jet behaved as a conduit, releasing pockets of volatiles built up through geological scale time. Some jets brightened sharply as solar storms bathed the comet in charged particles. Others bent and twisted in response to magnetic reorganization within the plasma envelope. Images taken after perihelion showed not weakening activity but intensification. The anti-sunward tail, once long and well-defined, grew more diffuse as expected. But the sunward-facing plume, already an anomaly, now strengthened. For reasons that baffled observers, the plume brightened even as the nucleus retreated from its closest solar exposure. It grew sharper in contour, longer in extension, as though responding not merely to heat, but to a deeper interaction between magnetic grains, charged particles, and solar wind. Such behavior implied that perihelion had awakened processes still accelerating after the moment of closest approach. The sun's energy had not only vaporized surface material, it had triggered internal transformations. Sublimation exposed deeper layers of ice mixed with metal-rich grains. Catalytic reactions intensified, generating more magnetite, more complex organics, more dust. Pressure in subsurface cavities rose, forming new fractures that became fresh vents for jets. At perihelion, the object was not being depleted, it was being revealed. Beyond chemistry, the perihelion passage altered the object's dynamical environment. Solar wind pressure peaked, compressing the plasma sheath on the sunward side. Magnetic draping increased sharply, folding the solar magnetic field around the object like a flowing cloak. Electrons and ions surged through the coma, creating oscillations that rippled through the jets. Under this external stress, the object's own induced magnetic environment likely strengthened. Magnetite grains released into the coma may have aligned more efficiently, amplifying the structured appearance of the jets and perhaps giving rise to new magnetic pathways guiding the sunward plume. During this period, observers noted subtle fluctuations in the brightness of the nucleus itself. These were not random flickers, but signs of rotational modulation and rapidly changing surface conditions. A 16-hour rotation meant that each region of the object faced the sun twice per day. In the extreme heat at perihelion, these exposures could have caused localized melting, followed by rapid cooling leading to thermal fracturing. Such cycles likely carved new vents just as older ones collapsed, producing a dynamic and evolving topography within the unseen nucleus. Another consequence of perihelion was the accelerated release of interstellar dust, accumulated during the object's long journey. As surface layers sublimated embedded grains, some ancient, some altered by cosmic rays, some containing the complex organics formed in darkness, were lofted into the coma. These grains, pushed by plasma flows and magnetic interactions, carried their chemical stories outward into space. For a brief interval, 3IATLAS became not only a visitor but a contributor to the solar system's dust environment. One of the most intriguing questions involved the transient presence of liquid water. Though the object never approached temperatures sufficient for long-lived liquid phases, catalytic interactions between metal grains and water ice could produce fleeting microfilms of water lasting seconds or minutes within pores just beneath the surface. These microfilms are known in meteorite studies to drive the formation of magnetite and other minerals. During perihelion, such processes may have occurred on massive scales across the surface of 3IATLAS, enabling complex organic synthesis at accelerated rates. The release of newly formed molecules in the jets supports this idea. If this interpretation is correct, perihelion for 3IATLAS was not just a physical turning point, it was the moment when billions of years of dormant chemistry briefly sparked into accelerated reactivity. The sun provided the energy, but the object provided the laboratory, the metals, the ices, the cosmic ray-altered organics, the catalytic structures born long before the solar system existed. After perihelion, the interstellar visitor continued to evolve. Its main tail dwindled as expected, Yet the Sunward plume, a paradox still unsolved, continued to strengthen. Its surface cooled, but not uniformly. Pockets of activity persisted. Jets erupted sporadically, suggesting that internal volatiles continued to reorganize as heat diffused outward. The coma remained bright even as the nucleus faded, and in the space behind it, a vast invisible trail of dust and organics marked the path of its passage. This trail, shaped and enriched during perihelion, would soon become relevant to Earth. But for now, in the days following its solar encounter, scientists looked at the unfolding data and realized that the interstellar object had not merely survived perihelion. It had been changed by it, chemically, magnetically, structurally, and in ways that offered profound insights into the nature of interstellar bodies. The Sun, acting as both sculptor and catalyst, had peeled away the ancient mask of 3IATLAS, revealing a nucleus with origins older than Earth chemistry, richer than most comets and behavior unlike anything planetary science had previously documented. Perihelion was the moment when the interstellar visitor truly became visible not just to the eye but to understanding. By December, the interstellar traveller had moved beyond the Sun's furnace. Its perihelion had passed, its jets had surged and then faltered, its ancient crust had been warmed, fractured and revealed. Now it was outbound, retreating into the colder geometry of the inner solar system. But as it receded, its path curved toward a moment of quiet significance, its closest approach to Earth. On December the 19th, 3 hours, Atlas passed nearer to our world than at any point in its long wander through the Milky Way. It did not pass close in the dramatic sense a near miss, a danger, a spectacle. Its encounter was gentle, distant by astronomical standards, safe by every measure. Yet the moment carried a weight disproportionate to its physical proximity. For the first time, an object that had left its birthplace billions of years ago drifted into a region of space where human instruments could study it with unparalleled clarity, and where the mind could consider not only what it was, but what it meant. As the object approached, telescopes captured its changing form. The anti-sunward tail, once sprawling across tens of millions of kilometers, had grown more diffuse, growing lighter and thinner as sublimation slowed. Yet the sunward-facing anomaly, that persistent magnetite-rich plume, continued to glow with increasing definition. It was a paradoxical sight, the part of the comet that should have weakened after perihelion, instead sharpened as if responding to forces deeper than heat alone. Against the backdrop of winter skies, Earth-based sensors tuned their spectrographs, hoping to capture the evolving signatures of a body that had begun to cool, but was still actively shedding the chemistry awakened weeks earlier. Every night of observation counted. The Earth moving along its orbit provided new angles, different sunlight geometries, and opportunities to compare pre- and post-perihelion composition. As the object drew nearer, the coma thinned but also clarified. Dust grains once too faint to study became bright enough to analyze. The structure of jets that had once overlapped grew easier to distinguish. The interstellar visitor offered for a fleeting time a window into its nature that might not come again for millions of years. Yet the scientific value of this close approach was matched by its symbolic resonance. For many, the idea that Earth was sharing its celestial neighborhood, even temporarily, with a body forged under another star, evoked a quiet sense of perspective. The object had travelled distances beyond comprehension. It had drifted through interstellar clouds, past exploding stars, through regions dense with cosmic rays, across the silent gulfs between spiral arms. And in this one brief moment it passed nearest to a small blue planet where life had emerged from molecules not unlike those carried in its dusty breath. The significance did not lie in danger, it lay in kinship. The kinship of matter chemistry and history shared across the galaxy. During this closest pass, astronomers searched for signs of fragmentation, spin changes, or volatile exhaustion. But 3IATLAS remained coherent. Its 16-hour rotation persisted. Its jets continued to pulse with rotational modulation, and its coma, though fading, remained active enough to reveal a nucleus still reshaping itself as internal pockets of warmth redistributed through its layers. Meanwhile, solar activity provided another unpredictable influence. Sunspots had rotated into Earth-facing view in patterns that coincided eerily with the object's trajectory, releasing bursts of solar wind and magnetic disturbances. Each geomagnetic pulse offered a natural experiment. How would the object's plasma cocoon respond? Would the sunward plume intensify further? Would its magnetite-rich dust align more strongly under the changing magnetic field? Preliminary images suggested that the plume brightened subtly during periods of heightened solar activity. Though the correlation remained unproven, the timing was striking. If true, it might mean the object was not simply a passive recipient of solar forces, but a responsive system reacting dynamically to the sun's moods. From Earth's vantage, none of this posed risk. The object's distance ensured that its dust posed no immediate threat, its jets no hazard, its gravitational influence no disturbance. Yet the Earth's proximity to this interstellar traveller ignited a wave of speculation. What material was it shedding into the space through which Earth would soon pass? What ancient molecules might settle invisibly into our atmosphere months from now? Not as a rain of meteorites, but as dust. Tiny grains formed in stellar nurseries far older than the solar system. For many scientists, December 19th was less a moment of caution and more a moment of connection. The Earth orbiting in its steady path had the rare opportunity to share its region of space with a visitor older than continents and oceans. And as they studied 3IATLAS, astronomers were mindful of another reality. This encounter was not the end of the story. The real intersection, the moment when Earth would cross the very region of space where the comet had shed its interstellar dust, lay months ahead in spring. But during the close approach itself, the object offered clues that would shape every question to follow. If the dust within its sunward plume contained magnetite amino acid precursors, cosmic ray processed organics, or volatile enriched grains, then Earth's eventual passage through its debris would become not merely an observational event, but an astrobiological opportunity. It might provide indirect answers to one of the deepest questions in science. How common are the building blocks of life in the galaxy? Meanwhile, as December's nights reached their longest stretch, the interstellar visitor grew dimmer to the eye. Its coma contracted. Its jets flickered as energy dissipated. Gradually the object began to regain the quiet it had carried across so much of its existence. The sun's influence weakened. The cold reclaimed its surface. The fracturing and boiling and swirling of perihelion faded into a gentler outward breath. But for a few days, only a few, it lingered closer to Earth than at any time in its vast history. Close enough that its dust tails could be mapped, its emissions tracked, its transformation witnessed with unprecedented clarity. Close enough for humanity perched on a small world, circling a modest star to contemplate the improbable journey of a body forged in a different sun's light. Close enough to remind us that the galaxy does not merely surround us, it travels through us one interstellar visitor at a time. As 3IATLAS drifted farther from the sun and the frenzy of its perihelion waned, Earth moved quietly along its own orbit, unaware at first of the intersection waiting months ahead. For while the interstellar traveller itself would be far beyond reach by spring, the space it had occupied during its moment of greatest transformation would remain marked by its passage. Dust does not disperse instantly. Molecules do not vanish into emptiness. Jets that erupted tens of thousands of kilometers from the nucleus carved wide invisible corridors of particulate matter into the fabric of the inner solar system. An Earth following its ancient path around the Sun would soon sweep through those corridors. This was not a collision. It was a crossing and encounter not with the object itself, but with the residue of its awakening. Between March and April, Earth would pass through the region where 3IATLAS had undergone its most intense cryovolcanic activity. This region, enriched by the object's perihelion chemistry, held dust grains from the deep interstellar medium particles, forged in cosmic ray exposure over billions of years, magnetite clusters born in brief moments of solar-warmed catalysis, and organics released into space when the object's crust fractured and boiled under sunlight. For a few weeks, Earth would exist inside the wake of a body older than its own star. To planetary scientists and astrobiologists, this moment carried rare significance. It invited questions that were not grounded in fear, but in curiosity. What kind of dust does an interstellar wanderer leave behind? How complex are its organics? What prebiotic molecules might be drifting invisibly toward Earth's upper atmosphere? And how often throughout Earth's history have such crossings occurred? Some of the grains in that trail would be tiny, less than a micron across, small enough to float through the upper layers of the atmosphere without burning. These particles, no larger than viruses, are the preferred carriers in theories of cosmic chemical exchange. Too small to incinerate, too fine to fracture, such dust settles slowly drifting downward across months or years. If the interstellar object carried sugars, nucleobases, amino acid precursors, or even polymeric organic fragments shaped by cosmic irradiation, they could survive the descent. They would interact not as meteors blazing through the sky, but as silent additions to Earth's reservoirs of atmospheric dust. For Earth, this is not an alien event. It is a familiar one woven into the story of life itself. Throughout its history, the planet has swept through countless cometary tails, meteoroid streams and dust clouds, each leaving microscopic traces. Some of the earliest carbon on Earth arrived in this way. Some of the earliest amino acids detectable in ancient rocks share isotopic markers with carbonaceous meteorites. For billions of years, Earth has been participating in a quiet exchange of materials with the solar system. What makes this encounter different is the origin of the dust. This dust did not originate from solar system comets shaped by thousands of orbits around the Sun. It did not form from planetary collisions or asteroid fragmentation within our local celestial sphere. It came from outside, from a body formed under another star shaped by conditions long vanished enriched with elements and compounds that had been altered not by the solar wind, but by the long, slow bombardment of the interstellar medium. A journey of tens of millions of years brought these grains into Earth's path. As the crossing approached, models predicted that dust density would be low, far below anything noticeable to the naked eye. No meteor shower would streak the sky. There would be no rain of bright fireballs, no glowing debris visible over continents. Instead, the encounter would be intimate and invisible, a whisper of particles gliding into the upper atmosphere, unnoticed by all but the instruments sensitive enough to detect them. And yet what those particles contain matters. Some may hold magnetite grains formed during 3IATLAS's rapid catalytic transformations grains that carry within them the chemical memory of interstellar travel. Others may contain simple amino acid precursors synthesized when the object warmed at 2.5 AU. Still others may be fragments of organic macromolecules built slowly across billions of years in the dark reaches between stars. In those components, scientists see hints of a galactic process older than Earth-1 that seeds star systems with the materials that under the right circumstances become alive. For Earth, the crossing becomes an elegant echo of its own origins. Early in its history, Earth was bombarded by countless bodies rich in organics, many likely interstellar themselves, during an era when the solar system was still forming gravity-chaotic dust clouds dense. Those impacts may have delivered the sugars, amino acids, and nitrogen compounds that later gathered into RNA. They may have carried the carbon that became the foundation for life. Now, billions of years later, the same process continues not violently but silently. This spring encounter becomes a reminder that Earth remains part of a larger system of exchange, one that is interstellar in scale and ongoing in time. Modern oceans, soils, and atmospheres still receive dust that originated around other stars. Tiny grains land on Earth every day carrying molecular fragments shaped before the Sun existed. Some burn, some survive, some settle into water droplets, some join soil, some drift above the planet for years suspended in the upper clouds. In the story of life, such grains are not foreign, they are ancestral. But beyond the scientific implications lies another question quieter and more philosophical. Earth's passage through the debris trail of 3IATLAS is a rare moment in which the planet physically intersects the wake of a body born in a different sun's light. It is a moment in which Earth touches the chemistry of another world, not a planet, not a civilization, but a wandering relic of cosmic history. Dust shaped before Earth formed now falls upon a planet filled with oceans and forests and awareness. A grain forged in the cradle of a vanished star may dissolve into a raindrop above a living world. There is something quietly profound in that, for in that crossing, brief, invisible, and delicate, we glimpse a truth that is older than biology. Life on Earth is not isolated. It is threaded into a galaxy where materials, molecules, and histories move from star to star system to system world to world. Earth's encounter with the debris of 3IATLAS is simply one chapter in an ongoing exchange that predates not only humanity, but the Earth itself. And long after the interstellar object disappears into the distant dark, the dust it left behind will linger, settling slowly, gently onto a world capable of understanding what it has touched. Long after 3IATLAS had passed its closest approach to Earth, after its coma thinned and its jets receded into the quiet of outbound motion, the scientific world remained fixed upon it, not through visible spectacle now, but through data. The interstellar visitor cooling once more as sunlight diminished had entered a stage no less important than its dramatic perihelion surge, the period of sustained monitoring, modelling and hypothesis testing. If the encounter with the Sun had revealed the object's nature, then the aftermath became the laboratory in which that revelation was studied. Every instrument available to planetary science now turned toward the interstellar object's retreat. From ground-based telescopes in Hawaii, Chile, the Canary Islands and Australia to spaceborne observatories orbiting the Earth, each platform gathered spectra, photometric curves and high-resolution images. Observatories coordinated nightly, comparing changes in brightness tail morphology, plasma signatures and gas emissions. Though the object was gradually dimming, the precision of modern sensors allowed researchers to continue extracting detail from its vanishing glow. The first priority was understanding the chemical evolution of the coma now that 3IATLAS was cooling. How rapidly would its unusual CO2H2O and COH2O ratios decline? Would the catalytic reactions triggered near perihelion persist for weeks afterward, and what organic compounds might linger in the dust as the jets weakened? Early post-perihelion spectra still revealed elevated carbon dioxide, though its intensity declined more slowly than anticipated. This slow decay suggested that deeper layers of oxidized volatiles continued to leak into the coma through fractures opened weeks earlier. Meanwhile, carbon monoxide emissions persisted at unexpectedly high levels, hinting that internal pockets of CO ice were still sublimating in the dimming warmth. These gases provided clues about the stratification inside the nucleus, clues that planetary scientists used to build models of the object's internal structure. One team using thermal modelling proposed that 3IATLAS possessed alternating bands of ice and metal-rich material, each layer recording a different era of cosmic ray processing. As the object warmed, each band sublimated sequentially, generating the changing emissions observed throughout its solar encounter. Such a structure would support the hypothesis that the interstellar object formed not in a single nebular episode, but through slow accretion of dust and ices across multiple environments in its galactic journey. Simultaneously, the sunward-facing tail, still visible though faint, became an area of intense study. Computational plasma simulations attempted to reproduce a plume of ejecta oriented toward the Sun. Dozens of teams tested models incorporating magnetite-rich dust-rotating magnetic fields, asymmetric solar wind compression and particle charge separation. Early results favoured a hybrid explanation: magnetite grains, entrained within a dynamic plasma sheath, may have moved along magnetic draping lines shaped by the solar wind, creating what appeared to be a sunward plume. To test these theories, researchers analysed polarization data measurements of how sunlight scattered off dust grains. Dust streams shaped by magnetic fields often exhibit distinct polarization signatures. Preliminary results indeed showed anomalies, polarization patterns inconsistent with purely gravitational or radiation-driven dust motion. If confirmed, this would represent one of the clearest instances of magnetic influence on the morphology of a cometary structure. Meanwhile, missions studying small bodies across the solar system contributed valuable context. Data from OSIRIS-REx, freshly analysing samples from asteroid Bennu, continued to reveal organic complexity and unexpected abundance. The detection of glucose, ribose, amino acids, and diverse prebiotic molecules on Bennu reinforced the plausibility that 3IATLAS, already possessing greater volatile richness and less solar processing, could carry even more abundant versions of these compounds. Researchers compared spectra from Bennu's sample with those obtained from 3IATLAS, searching for similarities in carbonaceous signatures. The results were intriguing. Certain spectral slopes and absorption features matched those of Cr carbonaceous chondrites and dark organic rich regoliths. These parallels strengthened the hypothesis that 3IATLAS was composed of materials from beyond any protoplanetary disk we have previously sampled. Each observation nourished the growing idea that interstellar objects could act as chemical time capsules, preserving organic chemistry from eras before the Sun's birth. Beyond spectroscopy, astronomers used orbital modelling to trace the object's path long after its departure from the solar system. Once 3IATLAS passed beyond Jupiter's gravitational influence, its outbound trajectory stabilized into a new interstellar course. This trajectory, combined with the Gaia DR3 database, enabled researchers to calculate where the object would travel in the next several million years and which star systems it might pass near. The modelling suggested that 3IATLAS would not approach another star for millions of years, Unless perturbed by unseen gravitational influences, it would drift quietly into the galactic night, carrying with it new layers of solar-imprinted chemistry. The sun, in warming it for one brief season, had altered the object forever. Simultaneously, Earth-based laboratories prepared for the March-April dust crossing, when the planet would drift through the trail left behind by 3IATLAS at perihelion. Instruments designed to collect high-altitude dust particles, including aerogel capture experiments and airborne spectrometers, were prepped for deployment. While expectations were modest, no scientist predicted a large dust density. The opportunity to sample even a handful of submicron grains could yield insights into interstellar chemistry without the need for a dedicated retrieval mission. Observatories also coordinated to detect meteoric signals in the upper atmosphere, faint ionization trails from dust grains, vaporizing at extreme altitudes. If detected, these trails would allow scientists to determine composition, indirectly revealing carbon content, mineral signatures, and isotopic ratios. Even a single detection could help assess whether the dust contributed by an interstellar object differs in measurable ways from that of solar system comets. Parallel to observational campaigns, theorists revisited a long-standing question: how common are interstellar objects like 3IATLAS? Recent detections, Oumuamua, Borisov, and now Atlas, suggest that such bodies may number in the billions across the Milky Way. Many may pass through our solar system unnoticed, too faint or too fast to detect. If each carries catalytic metals, organic inventories, and plasma-active surfaces, then interstellar exchange of chemical materials may be more frequent, more intricate, and more consequential than previously imagined. As more data arrived, scientists began refining the broader narrative. Interstellar objects are not inert. They are chemically active, physically dynamic, and capable of acting as organic reactors when warmed by stars. 3IATLAS demonstrated this dramatically. Its global cryovolcanism, magnetite production, sunward plume, and volatile-rich emissions marked it as a unique specimen, a living remnant of galactic chemistry awakening briefly under the sun. Finally, research teams turned their attention toward the future, the tools that would study the next interstellar visitor. Concepts for rapid response missions emerged, spacecraft capable of intercepting objects inbound, from interstellar space, sampling their outgassing, analyzing their dust, or even returning material to Earth. 3IATLAS, though already outbound, had provided the impetus for a new era of exploration, one in which humanity could study the chemistry of other star systems not through speculation but through direct sampling of wandering emissaries. As the object faded into the dark, the scientific world had not finished with it. It had only just begun to understand the lessons it carried. Its chemistry continued to be studied, its dust continued to be modelled, its mysteries continued to deepen. And the Interstellar Seed Hypothesis, once theoretical, now stood illuminated by the evidence left in its luminous wake. As 3IATLAS drifted outward into the cold, its coma shrinking to a pale haze and its jets fading into memory, the scientific community found itself standing at the threshold of something more elusive than data meaning. The interstellar wanderer had displayed its chemistry, revealed its mineral secrets, exposed the strange magnetism stirring its dust, and shed the molecular fragments of a journey older than Earth itself. Yet as it receded into darkness, the object seemed to leave behind not only physical traces but philosophical ones, for in the luminous arc of its passage 3IATLAS had shown a universe in which chemistry is not stationary but migratory, a universe in which matter forged under one star may awaken beneath another, a universe in which organic molecules shaped across billions of years drift through the galaxy in the silent caravans of dust-bearing bodies, like this one passing through systems brushing against planets and whispering stories far older than the worlds they encounter. Even as the interstellar traveller faded to a faint pinprick of light, its legacy remained anchored in the questions it raised. Scientists reflected on how its volatile ratios defied classification, how its nickel-rich composition echoed the rarest meteorites on Earth, how its global cryovolcanic activation transformed a quiescent body into a fountain of organics and magnetite. They pondered the implications of its sunward-facing plume, a phenomenon that challenged the very assumptions of cometary physics. They studied its dust, modelling how those tiny grains might fall into Earth's upper atmosphere during the coming months and what molecular signatures they might carry. All these investigations converged toward a single realization. 3IATLAS was not an exception. It was a representative, a member of a class of interstellar objects that almost certainly number beyond counting. Each one carries the chemistry of a different stellar lineage. Each one bears materials touched by cosmic rays, nebular condensation, and cold interstellar drift. Each one, if warmed by a star, becomes a vessel of catalytic reactions, producing or releasing organic molecules capable of seeding new environments. This recognition reframes humanity's understanding of life's potential origins. For decades, the origin of life on Earth has been studied as a local event, a moment arising from the interactions of water, minerals, energy, and time on a young planet. But 3IATLAS suggests a broader perspective. It hints that Earth's early oceans may have received more than meteorites. They may have received the molecular heritage of other stars. Dust from interstellar bodies like this one could have delivered sugars, amino acids, and nitrogenous bases long before biological complexity emerged. And if Earth was seeded in this way, then countless worlds across the galaxy may share the same inheritance. Interstellar chemistry becomes not background but ancestry. Yet beyond the scientific implications lies a quieter, more human reflection. To watch 3IATLAS pass through our solar system is to witness a fragment of the galaxy's memory, a relic of time before the sun's birth, carrying materials refined in the dark, drifting toward us by chance or by the inexorable geometry of celestial motion. Its journey reminds us that Earth is not an isolated island of life and matter. It is a waypoint in a cosmic network of exchange. The dust that settles on our planet may carry the signatures of places no human will ever visit. The molecules that fall into Earth's air may have formed near suns that burned out billions of years ago. And the chemistry that builds living cells on Earth may share origins with chemistry drifting now between the spiral arms of the Milky Way. As 3IATLAS continues its outward drift, it does so altered forever change by the sun. Its crust has been stripped, its chemistry has been awakened, its magnetite has grown, and its dust now carries new isotopic scars from the solar wind. It departs not as the same object it arrived, but as one newly sculpted, newly infused with the history of a star it will never see again. In that departure lies a mirror of our own existence, for humanity is shaped by forces it encounters, changed by environments in ways visible, and invisible transformed by encounters with ideas, data, and cosmic visitors like this one. 3IATLAS came, revealed itself, shifted our understanding of interstellar chemistry, and continued on. It asks nothing. It leaves no message except the one written in its molecular structure. But what it leaves behind is profound, the awareness that the galaxy is not static. It is circulating, swapping, mixing, carrying the potential for life's raw materials from one region to another. The universe is not silent in its exchange. It is rich with travellers. And in the wake of this object, humanity is reminded that the boundary between stars is more porous than we once believed. Now the object recedes, softened by distance, its brightness slipping beneath the threshold of human vision. In the cold, its jets quiet, its surface darkens, and the restless chemistry that once stirred across its crust settles into stillness again. Around it, the solar wind grows faint, and the gentle hum of the outbound space welcomes it back into the long night from which it emerged. There is no spectacle in its departure, only a slow, fading, a gradual return to silence. Yet something of it lingers, not in the sky, but in the mind. Its path remains traced in the memory of telescopes, in the data stored on servers, in the models that now hold its shape. And more than that, it remains in the quiet recognition that the universe is wider and older than the boundaries we draw around our star. The dust it released drifts softly through the inner solar system, settling into orbits, dispersing, thinning, until it becomes indistinguishable from the countless grains already circling the sun. Some will fall to Earth, dissolving high in the atmosphere, leaving behind molecules that travelled far longer and farther than any explorer. As winter melts into spring and spring into the longer days beyond 3IATLAS will fade entirely from view. But its memory endures an interstellar whisper passing through our neighbourhood, reminding us that the cosmos is not distant but interconnected, that stars share their chemistry, that worlds inherit the dust of ancient suns, that the seeds of life in their simplest forms may drift endlessly through the galaxy. And tonight, as the sky quiets and the stars settle into their familiar patterns, the thought of that travelling fragment now shrinking into darkness carries with it a gentle reassurance the universe is vast, yes, but it is also shared. Sweet dreams.